Good afternoon, everyone. I am Fadel Adib from MIT, and I will be telling you today about WhiteTrack, a motion tracking system that operates purely using radio reflections of our bodies. This is joint work with my amazing colleagues, Zach, Dina, and Rob. So this research is motivated by a simple question. Can we see through walls using wireless signals? If I shine a wireless signal at this wall, can I start seeing on my screen how people are moving behind the wall and tracking their motion? And the idea is quite simple. When I transmit a wireless signal, part of that signal is going to traverse the wall and reflect off everything in the environment, including our bodies. So can we use these reflections that come back to track people's motion behind the wall? Let me tell you what we can do using our system WhiteTrack. So I'm going to show you a video. And in this video, the person over here is going to be moving around in the room. Our device WhiteTrack is behind this wall. And in the bottom left corner of the screen over here, we see the output of WhiteTrack. Note the red dot. This dot is going to track the person as he moves. Now let me play the video for you. As you can see, the red dot is tracking him very, very accurately. And it does that without requiring him to hold any device, purely using radio reflections of his body. But this is not all we can do. Not only can we track the full body motion, we can also track body part movements. Let me show you. So he points at the lamp and turns it on. He turns it off. He turns off the TV. Now, because it works through walls, if you leave a room and forget to turn off the lights, all you have to do is this. So WhiteTrack has a large number of applications. Before I tell you about its applications, let me describe it to you. It can achieve centimeter scale localization accuracy purely using radio reflections of people's bodies. And it works even behind a wall and does not require the person to hold or wear any device. Now, in terms of applications, you could use it to extend gaming consoles like the Xbox Kinect so that they can track you even if you're behind an obstacle like a wall or furniture. You can also use it for gesture control, as I showed you in the video. And it has other applications, such as helping first responders find people before they go in and risk their lives, or in monitoring elderly. Now, in the rest of this talk, I'm going to describe to you how WhiteTrack works. We have a transmit and receive antenna, and we're going to send the signal from the transmit antenna. Now, a small part of that signal is going to traverse the wall and reach the person, and then it's going to reflect off the person's body and come back. And our goal is to use this very minute reflection to localize the person. That is, we want to know where the person is with respect to the device. So we need to compute distance. Now, to compute distance, we're going to use a very simple equation that we all know, which is that the distance is equal to the reflection time multiplied by the speed of light. So if we can get the reflection time, then we would get the distance. And the question becomes, how do we get the reflection time? Now, the most straightforward way to get the reflection time is to transmit a very short pulse. This pulse is going to get reflected off the person, and then it's going to come back. And the reflection time is the time between when we transmitted the pulse and when we received it. Now, in order to accurately get this reflection time, we need to know exactly when the received pulse arrives. So we need to sample the received signal very, very densely. In fact, to get the centimeter scale localization accuracy of WhiteTrack, we need sub-nanosecond samplings. This is problematic, because to do that, we need multi-gigahertz samplers. These multi-gigahertz samplers are orders of magnitude higher sampling rate than your typical Wi-Fi or LTE. And they are very expensive. And let's say you're willing to pay for them. They're going to give you multi-giga samples per second at their output. So you have an I/O problem to process them. Add to that they are high noise, and our signals are very weak. So for all of these reasons, they are simply impractical for our application. Now, to address this issue, we're going to borrow a technique from radar called FMCW, or frequency modulated carrier waves. Let me tell you how FMCW works. Instead of transmitting a very narrow pulse, we're going to transmit a signal whose frequency linearly increases with time. So as you can see here, time and frequency are linearly related. Now this signal will travel, and it will get reflected back after some time. And so we're going to get the received signal, which is a shifted version of the transmitted signal. But this reflection time is actually very hard to measure. Now here's the nice thing about FMCW. The transmitted and received signals are also shifted with respect to each other in frequency. So at any point in time, there's a frequency difference, delta f, between them. And if I can measure this delta f, then I can easily compute this reflection time. I just divide this delta f by the slope, and I know the slope because I'm the one who generated the FMCW signal. So the question becomes, how do we measure delta f? Now, to measure delta f, we need to subtract frequencies. But it turns out that subtracting frequencies is very easy. In fact, this is what you do when you remove the carrier frequency for Wi-Fi. So we all know that we receive Wi-Fi at 2.4 gigahertz, but when we process it, we only operate on the 20 megahertz channel. And the way we do that is that after we receive the signal, we remove the 2.4 gigahertz carrier. And in fact, to do that, we use a component that is called a mixer. It is low power, it is cheap, and it is found in all of our wireless transceivers. So to illustrate for you, what we're going to do is that we're going to get the transmitted signal and the received signal. We're going to feed them into the mixer. Now the mixer is going to subtract their frequencies, and so we're going to get a signal whose frequency is delta f. We're going to pass it through an FFT or a Fourier transform, and that's going to give us a spectrum. So now we get the power as a function of the different frequencies, and we get a peak at delta f, because that is our frequency content. Great. So now we can get delta f. We can map it back to the reflection time by dividing it by the slope. And from that, we can get the distance by multiplying the reflection time with the speed of light. So, excellent. Are we done? Unfortunately, not yet, because there's this problem that we always talk about in wireless, which is multipath. And what that means is that when I transmit a signal, it's going to reflect off everything in the environment. It's going to reflect off the human body, but also off tables and chairs and walls. So what's going to happen is, if I plot the reflection time as a function of the distance, I'm going to get something like this. So as you can see, there are all of these different peaks from the different reflectors at different distances. And I don't know which of them corresponds to the person, which of them corresponds to the wall, which of them corresponds to the chair, and so on. And so this multipath is going to mask the person's reflection. It turns out that this problem is actually not very hard to deal with. The key idea is that the wall and the furniture, these are static objects, so they don't move. And if I take successive measurements and subtract them out from each other, I'm going to eliminate their reflections. So for example, if I take a measurement at time t, I get something like this. Now if I take another measurement after 30 milliseconds, I will get this. Now, I will subtract these two measurements from each other, but before I do that, I want to show you that indeed both of these have pretty much the same multipath. Now, after I subtract them out from each other, I will get something like this. So as you can see, these very large peaks were eliminated. But something weird is happening. I still have two large peaks, which means that there are two moving reflectors, even though I have only one person moving in the environment. So why is that? These two peaks are 2 meters away from each other within this 30 milliseconds. Why do I have 2 peaks when I have only one moving person? The answer for that is quite interesting, and it's something we call dynamic multipath. So after I remove the reflections from static objects, I'm going to get the person's reflection that is going to come back directly to my receive antenna. But let's say there's a table. The person's reflection is also going to bounce off that table and come back to my receive antenna. And when the person moves, both of these reflections are going to change. And that is why I obtain multiple peaks. So how do I know which of these peaks is for the moving person and which of them is for the dynamic multipath? It's actually quite simple again. The person's reflection is going to come back directly to the antenna. So it's going to come back earlier in time, and it's going to travel a shorter distance. But the dynamic multipath, as you can see here, is going to travel a longer distance. And so I can simply choose the first peak, and this is going to correspond to the location of the person, and everything else is going to correspond to dynamic multipath. So this way, I am able to compute the distance to the person. So are we done? Well, not yet. Because this distance that I told you about is the distance from the transmit antenna to the person and back to the receive antenna. But this person can correspond to the person standing here, or here, or here. In fact, the person can be anywhere on an ellipse whose foci are the transmit and the receive antenna. And one ellipse is not enough to localize. So what we do in WhiteTrack is that we add another receive antenna, and from it we're going to get another distance measurement, and hence a second ellipse. Now we know that the person has to be at one of the two intersections of these two ellipses, and in WhiteTrack we use directional antennas. So we know that the person is at the intersection that is in front of the antennas. And so using one transmit antenna and two receive antennas, we are able to localize the person to a plane. Now, we also extend this to 3D by using 3 receive antennas. But over there, rather than having ellipses in a plane, we're going to have ellipsoids in 3D. And we're going to get the intersection of these ellipsoids to localize the person. So now that I described to you the basic components of WhiteTrack, let me tell you about its performance. So we implemented WhiteTrack, and in order to do that, we built an analog FMCW front end that acts as a daughterboard to the SRP software radio. And remember that FMCW is going to change its frequency, so we change it between 5.5 and 7.2 gigahertz in a manner that is compliant with FCC regulations for consumer electronics. And so we actually transmit very low power, sub-milliwatt, which is 100 times lower power than what your typical Wi-Fi access point is going to transmit. And we use one transmit antenna and 3 receive antennas organized in the shape of a T, and this will allow us to get the 3D location. Now, of course, to measure the accuracy, we need the ground truth. And for that, we use the Vicon motion capture system, which is typically used in Hollywood for tracking human motion and mapping them to a 3D model of the person. And so it gets you sub-centimeter accuracy, but it also requires instrumenting the ceiling with infrared cameras and putting on the person's body infrared reflective markers so that when he moves, you can actually track his motion. Now, in our evaluation, we asked the person to move at will inside the Vicon room, which is the 9x6 room, and we placed WhiteTrack about a meter behind the wall. So we use Vicon to create a 3D model of the person and compute the closest reflection point to WhiteTrack. And then we define our localization error as the difference between that point and the point as computed by WhiteTrack. So in our first set of experiments, we run about 100 experiments and collect 500,000 location measurements. And I'm going to show you the CDF as a function of the location error. So these are our results for x, y, and z dimensions. As you can see, our median accuracy is about 10 centimeters in x, 13 in y, and 21 in z. And the main thing to note from here is that we are able to achieve centimeter scale localization purely using radio reflections of the person's body and without requiring him to hold or wear any device. We also ran another set of experiments where we asked the person to point in a random different direction to, say, control an appliance. And I'm going to plot the CDF as a function of the orientation error. And this is what we get. As you can see, our orientation median error is about 11 degrees, which again is very accurate. We also wanted to test whether WhiteTrack can be used for fall detection in monitoring elderly. So today, fall detection systems require the elderly to wear sensors on their bodies, which many times they actually forget to wear, or to put cameras in their rooms, which they feel that they invade their privacy. So we asked the person to do multiple different activities, and we're going to plot the elevation, which is the z, as a function of the time. So when a person walks, this elevation is approximately constant because the person is moving at the same height. But when he simulates a fall, we see a very sharp decrease in elevation, followed by a location when the person is near the ground. And this is different from when a person sits on a chair because the final location is above the ground. And it is also different from lying on the ground, which is a slower motion before the person gets to ground level. And we run 133 experiments where we ask the person to perform each of these different activities, and our fall detection accuracy is 97%. This accuracy is the same as what you would get when you would require the person to wear sensors on their bodies. Now, WhiteTrack builds on multiple foundationally related work. And it is part of an emerging area that tries to use radio reflections for motion and gesture detection. And this includes YVI in last year's SIGCOM, YC in MobiCom, full duplex backscatter, OLC, which is the talk you saw right before me, and electronic frog eye in the upcoming Infocom. But in comparison to all of this work, WhiteTrack is the only one that gives you a location of the person. Now, of course, WhiteTrack is also related to more than a decade of work on RF localization. But it differs from all of that work in that instead of localizing an RF source over there or an RF transceiver, we're localizing the person using radio reflections of his body and without requiring him to hold or wear any device. Now, of course, WhiteTrack is work in progress, and we have some limitations. So, for example, it cannot detect a person unless he is moving. Because if a person is static, once it does the subtraction, it's going to eliminate his reflections when it eliminates the reflections of everything else. It also cannot concurrently track multiple people, and it only tracks one person. Now, as you might have guessed, we are working on lifting these limitations. And what I'm going to show you is some of our future work, where we're trying to remove the requirement of motion to detect the person. So, I'm going to show you a video of a baby. Over here, we have baby Chris, who is sleeping in his crib at night. And this is the output of our baby monitor. As you can see, even though the time is passing, and I'm not sure you can see, but in the top left corner, it's as if Chris is just an image. I cannot detect his breathing. But now, with our device, we can actually detect Chris's breathing. We can also track it in real time. So over here, Chris is inhaling, he's exhaling, he's inhaling. So not only can we detect him based on breathing, we can also count his breathing rate. And we do that using radio signals that are hundreds of times lower power than Wi-Fi. And you know what? It works even from behind a wall. With this, I will wrap up my talk. Thank you very much, and I'll take any questions.
One, just a minute to gather and come to the microphone while I ask a question, if I can sneak one in beforehand. Can you tell us a little bit just about the range of this system?
Yeah.
The coverage, like in particular, can you cover a house with a single installation?
Yeah, excellent question. So we actually demonstrated. Okay, so we tested it with up to 11 meters behind a wall. So this is our range, and we actually showed how the accuracy is changing as a function of the distance, because clearly as you move away, you're going to get a weaker signal. But in all of even when you're 11 meters away behind the wall from WhiteTrack, your accuracy remains less than 20 centimeters in X and Y and less than 30 in Z. So that is, of course, the median accuracy.
Is that a house? That's
I mean, it's about, depends whether it's in downtown Manhattan or, I don't know, it's in a suburban area.
Hi, should I be worried that the person in the hotel room next to me is just brought in a briefcase full of Wi-Fi equipment?
Yeah, so actually, I think the best way to address this issue is through regulations. You need the FCC to actually regulate how you're going to use these. And it's the same way as, I'm going to finish, it's the same way as today you cannot take a cell phone and take pictures inside a bathroom, right? That is not allowed. And there's also regulations for thermal imaging and so on and so forth. That said, if you actually care about that, you can design blockers. You understand how these signals work. They have a very specific structure. And you can try to block these signals. But I do believe that the best way to actually address this issue is through regulations.
The briefcase said FBI on the side, too. So.
Yeah, I wonder about blinds blowing in the window, and for that matter, the person in the next room moving around.
Yeah.
And to what extent can one easily filter out beyond the dimensions of the space or the areas you're interested in?
So the main thing to note is that what you do is when you have this, you are able to accurately localize the person as he moves. So of course, with WhiteTrack, when you had a person moving, you had other objects that are slightly moving in the environment, like we had a fan in the ceiling, you had, of course, the computer fans, and so on and so forth. And what these do is that they're going to add to the noise floor, but the person's motion is pretty much going always to be stronger. That said, in our upcoming work, hopefully, we show that you can eliminate everything and you can focus on different people, and that is how you can track them concurrently at the same time. Thanks.
Thank you.
Similar question, but I'll ask the second part, which is, I'm curious if, in addition, the robustness of your signal subtraction mechanism and how well it works if, for example, there are multipath, effects that may be attenuated as a consequence of somebody moving, and so there are multipath peaks that were there before, that are not there now. You could get multiple peaks, not just those two that you mentioned.
Absolutely.
Earlier, right?
But all of these other peaks that you're talking about are going to be traveling a longer distance. Because for you to be blocking a path that is already there, it means you have to be in front of it, right? Which means you have to be closer to the device. So still this first peak that you're going to get is going to be the reflection of the person.
And in the gesture recognition in the videos, there was a sort of a noticeable pause before the gesture was detected.
Yes.
Is that the segmentation mechanism
Absolutely.
you're using now?
So as you can see, like we can track the person when he's moving, and when he stops, you can track his gestures. We can track the gestures or the person, not both of them. So if I am moving and I'm trying to point in different directions, you're not going to get you're not going to allow me to control appliances.
Thank you.
Yeah.
Could you comment on how this is different from radar or sonar date back in the 60s, I guess?
Yeah. So of course we are building on radar techniques, right? FMCW is very much related to radar. But you have to realize that what we're doing is indoor localization, where you have all of this multipath around you. And so the goal is to get an accurate location of the person with all of the multipath. In the radar work that you're going to see, typically these things are done in open fields and so on and so forth, where you don't have all of this multipath that we get, and you don't need the centimeter scale accuracy that we are giving you.
If you had like greater degree to sample, do you think it'd be possible to distinguish organic versus inorganic reflection?
That's interesting. So you're trying to say, can I use some properties of the reflected signal in order, and we think that is possible, that is definitely part of our future work. And we think that you could even try to distinguish between people using different types of reflections by trying to characterize these reflections beyond just the location.
If I can ask
Yeah.
another question. Since you are doing this through the wall, the properties of the wall will affect the speed of RF in it, and presumably affect the resolutions or the accuracies of your distance measurement.
Yeah,
Any comments
so
on
the
that?
most important thing to notice is that we're not directly placing it on the wall. So I'm assuming you're referring to certain types of things that you would place this on a wall. This is at standoff distances. Let me finish. And what ends up happening is that this wall, its effect is going to be very small, And what you have to keep in mind also is that we're sweeping within a band where the properties are very similar to each other. You're not sweeping over whatever in 60 gigahertz between over a 10 gigahertz band where the properties of these signals are going to be different. So of course, at the end of the day, this is going to add some noise to your system, and this is indeed reflects in the 99th percentile of your accuracy, right? That is why sometimes you lose some accuracy. You don't get whatever. 10 centimeters, you get 20 centimeters, right? Because it's going to affect the distance measurement in some way.
So have you tried different materials like brick walls versus concrete versus wood?
Okay, so this is so in this project, our main focus was about how do you track through interior walls. So these walls that I'm telling you, these are double dry walls, which are with sheetrock on top, and they are separated by metal, right, in the middle. We have not tried with different types of walls, but you can also address that by adding a filter that will remove the wall's reflection, and so you are not affected by it.
Right, thank you.
Great. Well, let's thank Adib.
Thank you very much.